Hello, everyone. My name is Diaa Radwan. I'm part of the global Black Belt team in Microsoft, covering EMEA, focusing on Postgres and other open source databases. This session is building event-driven systems with Postgres, logical replication, and Drasi. In this session, I'll show you 3 ways to tap into that stream and build event-driven architectures directly on Postgres. We will run live benchmarks, compare real latency numbers, and look at working code that you can deploy today. As I mentioned, we will go through building event-driven architecture directly on Postgres. We will look into live benchmarks, working code, and practical guidance. So let's start. In the common scenarios, when you have an e-commerce application, you need to most probably you need to send an email when a high value order is paid. How do you detect that? And how you detect that change when it happens? Most teams start with pulling and running a query every few seconds, but you miss changes between pulls. You miss queries when nothing changed. Some use database triggers, but triggers run inside transaction. They block writes. They are hard to debug. Others do the double write, save to the database, and then send to Kafka, for example. But what happens when DB succeeds and Kafka fails? You get data inconsistency, the number one cause of bugs in microservice architecture. Going to the next slide, how we can solve that with the CDC. In Postgres, every insert, update, and delete is already being recorded in the wall. The wall is write-ahead log. Every row change in the wall, we just need to read it. No application code changes. Guaranteed delivery, captured inserts, updates, and deletes. There is no double write risk there. That's what we will see today. So let's get a little bit deeper here. With the wall pipeline, we have 5 steps. Application writes, wall records, every row changes, logical decoding, convert binary wall into JSON or PG output, depends on how you set up your environment. Consumer reads, and then downstream action. Postgres retain wall segments until the consumer confirm it has processed them. This is powerful, but also dangerous. We will come back to that. Let's go to the next slide. Sorry about this. So let's see how replication is working. So this is the configuration of the wall, how we can configure that. So this is three items that we need to configure. First thing, we need to change the wall level to equal logical. In some applications, in some providers, it requires a restart. If you're running on a VM, it requires a restart. Basically, this configuration, wall equal logical, this tells Postgres to include row level data in the wall, not just physical page changes. The second thing is the publication. This defines which tables to stream changes from. In this demo, we're using e-commerce app, like I said, so we have orders table because it is database for e-commerce. Think of the publication as a filter at the Postgres level. The third item and the last one is the replication slot. Each consumer gets its own slot. The slot tracks the position of wall. Again, the wall is write-ahead log. Now, let me show you the architecture of the demo that we will go through. I know this is a little bit busy slide, but bear with me. At the very top, we have here Postgres Flexible Server. You can run that in different Postgres if you want to take the code. You can run that as a Docker container, and then you have here the green box with 3 CDC streams. You have a wall stream, you have a Drasi in the blue box, and then you have the Kafka cluster. These are the 3 scenarios that we will go through. And then we have a load and dashboard. We are using low cost with 50 users simulating and generating traffic that will go through the benchmark table that we have. I have also Prometheus and Grafana, and we will not go through that to save some time today. The Postgres is the source of truth. and you can change that if you wanted to run your own environment. Also, remember, if you're running a external database, latency might be a little bit higher. Let's go to the next slide. Okay, this is too fast. Start with the first option. Okay, I forgot to talk about the Drasi option here. In the blue box, we have a continuous query filtering, and in the Debezium with Kafka, we have also Kafka Connect and Apache Kafka before reaching to the consumer. So let's go to the next slide, which is the putting things side by side to talk about the environments that we will go through. So we have same Postgres source, 3 different paths, all writing to the same benchmark events table, and this is how we get a fair comparison. Same load, same data, but different architecture for each scenario that we have. The first one is Volta.json. Let me describe how this is go. The first one, we have 4 steps: wall to plugin, then to consumer, to database, no middleware, direct connection right away. Let me switch to my terminal here, and let me give you first what's the Docker containers that we have. So we have again the Kafka Connect, and also the some exporters for the monitoring. On Kafka and Debezium, we have the broker, we have the Connect and the UI, and also we have the Streamlit dashboard that we see the results of the environment that we're running. Before that, I wanted to show you the database that we have. So this is the benchmark table. We don't have a lot of things to show because we didn't run anything yet. Now, checking how the orders looks like. This is the source of truth that we have. So we have the customer ID, we have the amount, we have the status, and the status can be new, shipped, and paid. And this will be important because we will talk about filtering later on. Let's see what's the distribution of the data that we have today. So we have different status for the canceled, new, paid, and shipped orders. It ranges from, the amounts range from 20 to 2,000. Okay, let's start with the first one, option that we have, and this is Volta.json. So now we're starting Volta.json and also starting the low cost. And when we start low cost, it will generate some traffic, read from the order table to the benchmark. This will take a couple of minutes. We have 2 minutes run for each workload. So as you can see here, Volta.json is running. The median latency is 2 milliseconds, and low cost is starting to push the data inside the benchmark table. So now this is moving. This is good. This is a live demo that we're having here, and we'll do that for the different scenarios, Debezium and Drasi later on. Let me continue going through the presentation. And when we go through the presentation, I'll cover a couple of things to give you a little bit deep dive on how things are running. With the Volta.json plugin, it's converting the binary wall records into JSON. It is a custom output plugin installed on the server. The key benefit here right away is simplicity. It's just what Postgres has. And one risk, it is one slot, one consumer, no replay, and no fan out. If you have five downstream services, then you need 5 replication slots. This is 5 times the wall cost. Drasi solves this differently. One slot, but multiple queries, multiple reactions inside Drasi. Fan out without extra slots. In Debezium, it is solved with the Kafka. One slot into Kafka, then unlimited number of consumers and groups. So this is a critical design choice. So let's jump into the Volta.json use cases. And this is the good fit when it comes to audit trail. You wanted to steam every change to compliance store or cache invalidation, for example. or you wanted to do search sync, so you keep Elastic Cluster and Postgres in sync, or real-time ETL. Also, if you wanted to have single service webhook, fire an HTTP call per change, for example. But Wall2JSON will not be suitable if you have multiple consumers that need the same stream, or you need replay. I think our benchmark finished already. Let's go through it. Let's read now the latency numbers. The latency is around 2.5 milliseconds. So this is good, and that's as close to the middle as you can get with logical replication. No broker, no middleware, just Postgres and Python. And when we go to Postgres here, let's see the number of records that we have. So it's around 3,500. So this is good. Let's jump into the next scenario that we have, and this is with the Debezium and Kafka. So in the Debezium scenario, we have 6 steps: wall to PG output, to Kafka Connect, then to Kafka Consumer, to the database, 2 extra hops. Let's see what the cost of that. I'll return back to the terminal and fire up the scenario of the Debezium, and I'm launching that as we did before. What will happen that it will bring up the environment for Debezium and at the same time open up low cost, and then we will see the whole changes happening and the traffic going to the benchmark table. So low cost is up and running now, and let's see how it looks like on our low cost environment. Starting now. Okay, so it started. Yeah, more traffic is coming. We have a couple of response time, and also the number of users that we have is 50, as we mentioned. Quick comparison here between Wall2JSON and Debezium. You'll see big difference between them. You can see Wall2JSON is low here, while the Debezium is there. This is because of the 2 hops that we have. It is around 600 milliseconds or 500 milliseconds. So it is way bigger than the Wall2JSON. So let's go to the presentation to get into the details. So Debezium is the industry standard. They changed this for the change data capture. It reads a Postgres wall using PG output protocol, but instead of going direct to change it goes through the flow. The flow goes to Kafka Connect into Apache Kafka topic, and our Python consumer then reads from Kafka. You get schema of evolution, multiple consumers groups for event replay. That's a lot of capabilities, but it comes with cost of infrastructure. In going through the full Debezium pipeline includes Kafka Connect, schema management, and connector configuration. It is the right choice when you already have Kafka, or when you need multiple teams consuming the same event stream. Let's go to the use cases of Debezium. Of course, it's very obvious: microservice event bus, many teams, many consumers, one stream that you want to have. Event replay for new services, joins, replay, and replays from offset 0, cross system sync, and also is very important to know that if you're using, if you wanted to have one consumer, then Kafka would be overkill, and if you wanted also sub-millisecond latency, you don't want to operate Kafka. This is one of the reasons why you don't want to use Debezium plus Kafka. Okay, I'm going to the Kafka UI. Here we see the our topic. Okay, does work, but our low cost finished, it's still running. If I updated the Streambed benchmark that reads from the table that we queried a couple of seconds ago, we'll see that we have Debezium and Wall2JSON. I'll cancel Wall2JSON. See that is going through the around 500. So now with the Debezium, it is finished. It's around 500 milliseconds. This is good. Going through the PSQL, now we see the same amount of events that happens. Both of them doesn't have any kind of filtering. It is only the events that we got from the orders table. Okay, I'll move to the next topic here, in which is going through the Drasi. We need to note on the Kafka thing is not slow, but it's 3 times higher. This is direct path. In the trade-off that you get durability, fan out, and the entire Kafka ecosystem. Now, what if you don't want to every change, just the changes that matters to you? This is where Drasi comes in. So with Drasi is a open source data change processing platform from Microsoft. It is now a CNCF Sandbox project, and it lets you define continuous queries that react to a data changes in real time without writing streaming code. Drasi has 4 steps. It is the same as Wall2JSON, but step 3 is different. Instead of shipping all events, Drasi runs a continuous query. It only emits events that match our filter. So let's go to the terminal again and launch the Drasi use case, and it will do the same. It will bring up low cost, and it will write to the benchmark table that we have. So this will take a couple of seconds, and we go to the CDC again for the benchmark, and you see 2 things here coming up: Drasi and Drasi filtered, because Drasi, we can see the filtered option, which is the $500 orders and 2 status. So I'll exclude the Debezium because the Debezium is too high. I will skew the whole environment. So you see Debezium and Drasi filter playing in the same ballpark. It's around 2.5. Low cost still running here. So until that finish, I'll go through the presentation once again to go through the Drasi deep dive. So Drasi uses 1 replication slot, just 1 replication slot, but it runs multiple continuous queries against the single stream that we have. We have 2 queries right now: 1 capture all the orders and 1 filter high value orders, like we said. That is amounts with $500 or more for the orders that paid or shipped. Each query can trigger different reaction: webhook, gRPC, HTTP, all from 1 slot. With Wall2JSON, to do this, you'll need 2 slots and 2 separate consumers. This is twice the wall cost. Drasi evaluates every change against all active queries. If it match, it emits. If not, it will be filtered out. Drasi supports Cypher and SQL queries. It is Kubernetes native. For the source queries and reaction, they are all in declarative config. So it makes things easier to add additional runtime tools without redeployment. There is also some trade-off. It's a new project, and there is no durable event log. If you need replay, you need to add Kafka. Let's go to the use cases of Drasi for fraud detection, for example, SLA monitoring, dynamic business rules, and also a multi-query fan out in condition notification. It is similar to the case that we have where you wanted to email only VIP customers with high value orders. Drasi will not be suitable if you wanted durable event log. You will need to add Kafka instead, or Kafka plus Drasi. And if you wanted to have a broad ecosystem connectors, Debezium, for example, has more than 50 sync connectors, which make it very rich. So let's go to the terminal. Hopefully, Drasi will be finished. If we go through the approaches, you will find that we have around 5,000 events. We have 1,500 or 1,600 um, filtered orders. So now with all of this, what we can see here with Drasi, we can see the orders that we have and see the grouping of the filtered and unfiltered ones. Let's do this. So we see with the Debezium and Drasi, they are the same event numbers, but the filters around half, and the captured and the average milliseconds. As you can see here, Debezium is around 500 millisecond. Drasi is around 3 millisecond. Voltage is 2 millisecond. When we read the demo results, what you see here is the same query that we ran, and if we compare that with the CDC pipeline that we have for the benchmark, you'll find that Debezium is going up. I'll filter out Debezium. Sorry, filter out Debezium here and add Drasi. You'll find that they are around the same timing, but you add filtering with Drasi. So going to the results here, reading the benchmark, we have 3 approaches, same workload, 50 users each, 2 minutes run. The latency first. It is the benchmark that I run for this slides. It was 1.5 because I used Docker container, not external Postgres. So Postgres externally will add a little bit of latency. It is around 2.5 to 3 milliseconds for both voltages and Drasi. With the Debezium, it is 500. Kafka, of course, add a broker time plus the consumer polar interval. This is 300 times slower, but slower is not worse. It depends on what you need. Drasi has more because it writes both filtered and unfiltered. So about 5,000 high-value orders that we filtered out. Only Drasi can do that filtering. Voltages and Debezium show 0 filtering. In comparing also replication slots, you'll find voltage is 1 slot per consumer. If you wanted 5 consumers, this means 5 slots, and this is 5 times the cost on word retention. Drasi has 1 slot, multiple queries, multiple reactions. Fan out happens inside the Drasi. With the Debezium, 1 slot into Kafka, fan out via consumer groups. This is a big deal in a production system. And on infrastructure complexity, voltage in just Postgres. Drasi is using Postgres and Drasi server. With Debezium, you have Postgres plus Kafka plus Zookeeper plus Kafka Connect, which is a little bit a lot. On code side, voltage is around 150 lines of code. Debezium is around 120. And Drasi around 180, including the declarative language that we were using. There is no single winner here. It depends on your requirements. Let's go to the most important thing here if you're running in a production environment. All 3 approaches use replication slots. If your consumer dies, Postgres keeps accumulating WAL. It will not release these segments until the slot confirms it has processed them. This is the strongest part, but also it is dangerous. And here's what happens. If consumer pauses for network issue or crash or new deployment, slots stop advancing. Postgres retain all WAL since the last acknowledgement. An hour later, your disk fill up. Postgres goes to read only. All writes will fail. I've seen 64 gigabytes of WAL accumulate in 1 hour under moderate load. A single forgotten slot can take down the production environment. So how we can protect our systems against it? 3 things. The first one is max slot wall keep size. We keep that. We make sure that it is not -0, so we can free the wall. This is first thing. If you're running flexible server, it is -1, so make sure that you change that. The second thing is monitoring and query PG replication slots regularly, and check the wall lock column and alert when exceeds your threshold. Third one is drop stall slots. If a consumer has been dying for an hour, drop that slot. It is safer than filling up the disk. Let's go to the last slide that we have, and this is around the guidance and which solution to pick. So you use Wall2JSON when you have single consumer, one slot, one reader. You want simplest setup, audit log, cache invalidation. But remember, no fan out. Each new consumer needs its own slot. Debezium used plus Kafka. You have multiple consumers. You need multiple consumers that needs the same event. You need the event replay or microservice event bus. When you use Drasi, you only care about specific data pattern, high priority alerts, or you wanted to have rules and to change at runtime. A quick decision flow, need fan out or replay, Debezium plus Kafka. Need server-side filtering, this is Drasi. Single consumer, all events, simple as possible setup, this is Wall2JSON. If you're not sure, start with Wall2JSON. It is the easiest setup and easiest to migrate from. So you can add the Kafka or Drasi later. Also, you don't always need a streaming platform. Sometimes the database that you have is already enough. You can download all the code for this demo from my GitHub repo. You can see the link down here, and and hope this session was beneficial to you. And thank you.